Day 68, page 272, problem 56, rotational kinematics. Here we have a cylinder with a thread pictured here on the left, side view. The thread is being held onto by a monkey of 1 kilogram, and it's pulling down. The monkey is accelerating down, and the cylinder is accelerating rotationally. And when we draw these free body diagrams, you've got to be really careful in making sure you put on a rotating object, you want to make sure you put the forces in their proper spot so you can see where the torques are and so forth. For example, here's the tension on the outer rim of the wheel at a radius of 10 centimeters, R sub 1 I'm calling that, causing the rotational acceleration of the cylinder. Bottom line is, well, a couple of background pieces of information. The rotational inertia of a solid cylinder is 1/2 mr squared. And the general relationship between linear acceleration, tangential acceleration, and rotational acceleration, A equals R alpha. But bottom line is, it's basically, in a sense, Newton's second law. If you look at the monkey, it's F net equals ma. Monkey has two forces, the force of gravity down, 9.8 newtons, minus the tension, which will be smaller than 9.8, equals m sub 2, mass of monkey, times his acceleration or her acceleration. And then the same idea and principle to the cylinder, the net torque equals the rotational mass, I, moment of inertia, rotational inertia, times the rotational acceleration, alpha. And then torque is force times distance. The force that's creating the torque is the tension in the string times the distance from the center of rotation. So the torque is, this stands for tension, not torque, this T right here. So force times distance for the torque generated by the string the monkey's hanging on to equals rotational inertia, 1/2 mr squared times alpha. So now you just do the math there, simplify, you get the tension is m1, n sub 1, r sub 1 alpha over 2. Same thing over here, reduce this, solve for T, plugging in our relationship between linear and rotational acceleration down right there, getting rid of the A. So you have R sub 1, that's once again the radius of the cylinder, times alpha. And then solve that for, well, you have that solved for T. And then we have T equals this, and T equals this. So both of those two things must be equal to each other. So I'm bringing this over to here, equal to this coming down here. And basically moving things around, plugging things in. The only thing we don't know is alpha. So you can see here, if we solve through all this, just go through the algebra. Alpha, the rotational acceleration, is 16.3 radians per second squared. Now we're looking for the linear acceleration of the monkey. So you could just take that blue circle at the bottom and plug it up here at the top. Plug that in for alpha right there, times the radius, which is 0.1. So the linear acceleration is just going to be 1.63 meters per second squared. And then you need to find a tension as well. So you can either use this equation, now that we know everything. We can just plug in the numbers here, because we know m, r, and alpha. Or over here, m sub 2 and a. In either way, you'll get your tension. It's right around 8 newtons, just over 8 newtons when you plug that all in.